element T is integral over R. You know, T is a root a monic. And we'll see in a moment why monic comes up and prove polynomial. And again, as for last time, this is what it means for a single element T to be integral. You plug it into that polynomial, you get 0. And we say that T is integral over R, the entire extension T is integral over R, if every element of T is integral over R. So, there was all this business about, T is an R algebra and so forth. Why would we care about this? Well, here's an example. And this is an example that's sort of playing around in some woods that I'm really not going to play in that much, but I think it's good to bring it up. So let R equals, say, Z, and T let T be the root of 2 by 2 meters over Z, right? So notice, of course, T is an R algebra, right? R is commutative, T is not, right? And remember what it means is this has to be an R module, a Z module, which of course it is, right? And there also has to be a homomorphism from R into T that takes the identity of R to the identity of T, and the image of R under this homomorphism is a commutative subring, right? Well, here's the way the homomorphism works. We'll call this phi of n is n times the 2 by 2 identity, right? And so you can see that there's an isomorphic copy of Z sitting inside of this ring. It's in the center of the ring. That's what I meant to say earlier, I think. Yeah, so the image of this is actually the center of this, right? Let me give you a serving example of it. Integral note that if we identify Z with then notice that for all M and Z, the matrix 0M 0 0 squared is 0 0 0 0. Right? So in particular, so each matrix of this form is a root of x squared is the 0 matrix, right? And this is identified with the subring R, right? And so this is kind of a disturbing example, right? Because here we have a degree 2 polynomial that has actually infinitely many roots, most of which are non-zero. Right? Okay. Here's some other examples. Notice that the complex numbers is a linear extension of the reals, and of course, I is integral over R. In fact, it's a root of the polynomial x squared plus 1. And in fact, I is integral over z. All roots of x to the fifth plus 2x plus 2, which I know is irreducible because this is an Eisenhower polynomial. All complex. Are integral over z. And of course, I think I pointed out last time, anything is integral over itself, right? So, because if you have an element of the ring itself, it's a root of x minus r, right? In a very silly way. But not z or q, because in fact, pi is not even algebraic. However, pi over pi is integral over right. Notice that what this is, let me kind of make it familiarize. This is the smallest ring that contains all the integers and also the element pi squared. So this a typical element of this is these are all sums that look like this. M to K pi to K. And notice the pi is the root of this polynomial. Here's another example. But R equal find all elements of P anybody want to take a guess at that? Full RC. So I claim where Q bar is the algebraic closure. Are y'all familiar with algebraic closure? It's the set of all, well, in this case, we'll take a set of all complex numbers that are algebraic. We'll get to this later. I'm not gonna be too careful about this yet. I mean, it sounds like something good to ask in the future, perhaps. But so, suppose you have something here that, or I'm sorry, something here that's algebraic over this, right? Actually, it suffices. Notice, let me point out that anything that has a zero constant term is already in here, so it's already in it, as a matter of fact. So all you really have to do when you realize that this is really c plus x cx is focus on which terms out of here are algebraic over here. Right? And you can do this by doing a homomorphism that annihilates x, and see if you can show that carefully, that the elements that are integral are in fact algebraic over here. Let me point out also, algebraic allows non-zero. Well, let me kind of do it in detail here. So suppose, let's say z plus x fx, and then cx. So z is in c, and fx. Right. Now let's suppose that this is algebraic over. I'm sorry. Let's suppose that this is. Let's suppose that this is integral over r. Right. So. M plus. Let's say r n minus 1 x. Let me think what I mean by this. Suppose this is 0, where the RI's are actually this is what a modern polynomial looks like over R(x), right? Now, the first thing that I would like to do is let x equal 0. Let's reduce this equation by letting x equal 0. This is a homomorphism, actually. And the image of this homomorphism lands R down in Q and P in complex numbers, right? What is this? When I annihilate x here, what do I get? I get Zn plus Rn minus 1, 0, Zn minus 1 plus R1, 0, Z plus R0, 0, 0. And now each Ri of 0 is in Q. Right. So C is integral. So in particular, algebraic over over Q. And there you go. So that means that Z must be in Q bar. And that shows that anything that's integral is actually contained in here. Now, the other way around is pretty easy to do, actually, right? So showing the contained the other way is actually the easy part. Okay, any questions? One more example. Every element of Gaussian integers, this is a old friend to some of us, a plus bi, a, b, and c. And I think when I demonstrate to you why this is true, you're going to see how to generalize this. A typical element of the Gaussian integer looks like this. And so notice that so I'm gonna do this a couple ways. First thing I'm gonna do is I'm gonna bulldoze this, right? I'm just gonna run right over this. Everybody okay with that? And so notice that now all I have to do is place some linear algebra names, right? Now, here's what I mean by playing linear algebra games. If I want to put this together in a polynomial, notice what happens here is if I take x squared, got this thing. Now, to make this balanced, because remember, I want this to be zero, I've got to get rid of the complex part, right? Or I should say the imaginary part. And so if I multiply this by minus 2a, this is going to be that's going to give me minus 2ab. So what happens when I have x squared minus 2ax? I'm going to have a squared minus b squared as I 2ab minus 2a of this minus 2a minus I 2ab. So I'll put that together. Right. 2a squared. Thank you. Convenient. So that's going to be, let's see, I guess minus 2a times this, right? Minus 2a times, okay, good. And so really what this gives me is when I add this up, I'm going to get minus a squared minus b squared, right? So at this point, I should have minus a squared plus b squared. And this thing should be a root of this equation, right? Now that's the bulldozer method. There's a slicker method, and that is, this is for fans of Galois theory, I guess, but you don't even need this because this particular ring, this must be a root of a polynomial with coefficients in the integers, which of course this clearly is. And I don't know much, but I do seem to remember that when I have coefficients over the integers, or in particular the reals, then my roots have to occur in complex constant pairs, right? So thinking about that from that perspective, that should be in a certain sense the irreducible polynomial. So what happens when you multiply this out is you get exactly so let's slicker a little bit more elegant without the bulldozer, right? Now, I guess what I've convinced you is this. I hope that if you have any a plus b out where a and b are integers, then it's integral, right? Because there's a small whole, right? Are there any others? Right? So every element of this, so here's a question. If you look at the quotient field, if I allow A, B, B, and Q, but not Z, can be integral levels. And actually even or there are still be elements in the Z. Right. Right. Because let me give you kind of an analog. Right? Consider right. I mean, really, the quotient field of this is Q adjoined with the square root of -1, right? What if I have this? Notice that if I have this thing is integral also. Right? Let's do the fancy pathway. Okay, let's see what happens here. In the middle term, it should be minus, it's x times this, and x times this. Notice that this imaginary part cancels out, right? And so this should be 1/2 x, this is x. And notice the product of these two, because this is a difference, well, this is a plus b, a minus b, then it should be the square of this, which is 1/4. And it should be minus the square of this, which is minus 3/4. So we get 1/4 minus 3/4 is 1. So now, not just integer part, we've got that 1/2 floating around. Actually, the answer to this question is no, or there aren't any more. That's a complete list of the integral elements over Z in that field. This one has some more, right? And it's a number theory thing. It depends on whether or not what you're adjoining into that radical is equivalent to 1 or 2 or 3 mod 4, right? So let me give you kind of a little bit of a spoiler here. So hopefully we've got some examples there to give us on our feet about integrality, right? Obviously they're all over the place. Now let me point out something that I think is not obvious, right? Let me give you here. Square root of 3 and square root of 2 are both integral over Z. This one is your x squared minus 2, and the second one is your x squared. 2. What about some of the products? Well, the product of these two, radical 3 and radical 2, I think is pretty obviously integral over Z. right? X squared minus 6. What about the sum? What about radical 3 plus radical? Notice both of these are square integral, right? They're minimal polynomials. Quadratic. What about this? You can do this actually the same way that you did before, right? But it's not obvious as all it works. So if I have x equal radical 3 plus radical 2, then x squared is, and I'm going to get a shortcut. I'm going to get lucky. Because if I look at x squared, I'm going to get 5 radical 6, correct? And I'm going to forget to stick to cubic because I know what's going to happen. X4, take the fourth power of this, is 25 plus 24, which is 49. And this is going to be 20 radical 6. And now my linear algebra works out pretty nicely because if I look at x to the 4, that's this. I've got to wipe out that radical 6, so I'm going to need minus 10x squared. And where am I on my constant? So now at this point, I've gotten rid of the radical 6 part. So in tandem with this, I've got 49 minus 50. So I'm at minus 1. There's your monopolynomial, right? And you can do that by, actually, you can do Galois because the images of this are, there should actually be 4 roots to that thing. And the roots are this, minus this, and then radical 3 minus radical 2, and minus radical 3 plus radical 2. And if you take those 4 and put it in, you get it, right? But I did get a little bit lucky at this step because I didn't even have to use the cubic, right? And I mean, even over the integers, take and beta. One of my personal polynomials. Beta is the root of this one. These are both irreducible. By the way, I know both Eisenstein. So by definition, the first one, they're irreducible polynomials. The first one should have 5 complex roots, and the second one should have 13 complex roots. I picked one each, alpha and beta. Is the sum the root of some monic polynomial? I mean, we do know it's a root of I mean, if you remember something like 8520, or if you had any Galois theory or something like that, you might remember that it's a root of some, it's an algebraic, I guess. Is it clear it's monic? And before you say yes, I'll ask you what's the polynomial, right? And then you're in Jim's world of pain, right? For sure, because I'm quite sure it's a mess, right? Not clear that the sum multiplies. However, it is true. And so let me give you this theorem. It turns out that integral elements, sums and products, integral elements actually form a ring. And so here is kind of the key theorem here. And I'm doing this in a little bit more generality than I usually actually do in practice, but what the heck. 313, let R be commutative T in R algebra and U and T. With 1. T of R algebra and U and T. The following conditions are equivalent. Number one, U is input. And two, there's a finitely generated R submodule. Submodule A contained in T, such that UA is contained in A. And here's the technical condition. Electrolyte or of A and T at 0. And so, for example, if you're in a domain situation, okay, let's go through this. So here's the wonder of this theorem. U is integral is a condition that by definition it's a root of some monic polynomial, right? Monic polynomials can be a mess, as we've sort of explored, right? The fact that this implies this is fairly straightforward, right? And we'll show that briefly. But here, really what this means is basically all you need is a finitely generated module such that U times A is still an A. And that gives you, you don't have to worry about coefficients or anything, that gives you the existence of it. The two implies one is really the interesting part. For the first one, I'm just going to demonstrate what the module is. Let's let A. So I know that U is integral. Some monic polynomial of degree n x to the n or n minus 1, n minus 1 r1 r0 and these r I and r. So let A be the module generated by 1 u squared u n minus 1. Now, I claim that UA is an A, so let me demonstrate that really. So what does it work? I mean, I think we'd all have to agree with that in fact, UA is generated by those n elements where I'll kick the power up by 1, right? But because of the fact that this is integral, I actually have this is equal to minus Rn minus 1 Un minus 1 minus R1U minus R0. And so this thing right here is in A as well, right? So the upshot is the reason UA is in A is because these first generators are in A, and the UN can be expressed as a linear combination of the lower powers, and therefore is in A. So the integrality works wonders here. And of course, you see the monic actually is kind of important here because you actually need that UN, the next generator. You can't have constants in front of it. There could be hazards there. You need that in those terms here. But the monic's really important in the other direction. Before I do the other direction, I want to do a little linear algebra. I was looking at my notes this morning. It's like, which class am I prepping for? Because we did this kind of stuff in linear algebra a little bit later. Suppose, so so we'll call it preliminary. 4 2 plus 1. So this is a little blast from the past. This is linear algebra. This is sort of, you probably saw this at some point, although maybe in passing, and you might have thought it was silly. Suppose that M is an n by n matrix. And I'm going to let this be the adjugate. How many have you heard of that before? Or the classical adjoint? I'll tell you. Sometimes I think this is called the adjugate, or this is classical adjoint. I call it classical. The Beatles did it or something. So anyway, this is defined to be, so I'll accept remember. So the classical adjoint is the transpose of the cofactor matrix. Where the cofactor matrix the ij entry of C is -1 the alpha plus j C I j, where Cij is the determinant you get by deleting the ith row and jth column. So what you do to compute this cofactor matrix is to have the ij entry, take your original matrix in, delete the ith and j, or the ith row j column, compute the matrix, and that gives you some, or I'm sorry, compute the determinant, and that gives you some number, and then -1 depending on the parity of output, right? And then the classical adjoint is the transpose. So that is to say, how many of you have, is this ring a bell? Like maybe from, you know, layers of therapy haven't gotten to yet or whatever, but it's back there somewhere, right? So it's not difficult. And in fact, I know because I at least sketched the proof of this even in 3110, that M times the classical adjoint. This is one way that you can sort of get an inverse, so to speak, is determinant of M times IN. Well, IN is the n by n identity matrix, right? So in fact, the classical adjoint is one of the things that I'll teach in 3110. It's sort of an alternative to finding the inverse, right? Because notice that M is invertible if and only if the determinant is non-zero, right? So you kind of get this bonus out of it. But if M is invertible, then this is non-zero. And so you can see from this that if you take the inverse of this number and multiply by the classical adjoint, you get the inverse of the matrix M. But the advantage to this formula is, of course, you could say, well, the classical adjoint is just the inverse, right? It's just the inverse of m, you know, adjusted by this thing. But of course, this works even if m is not vertical, right? So I'm going to use this fact. So this is all kind of old in your algebra. Suppose m times here a1, a2, and n is equal to x, a1, a2, and n. So suppose that I have this, and so that is to say x is an eigenvalue. Well, let's say x a1 to an is eigenvalue eigenvector. From matrix M. Then what we have is m minus xi times its vector is equal to 0. So if we multiply by the classical adjoint, so multiply by the classical adjoint, then what we get is determinant of right n minus xi times in times that vector is equal to 0. Agreed. And so really what that means is, so in particular, because after all, this is constant, right? This is just some number, annihilates. All of it, right? Because basically this number times a1 has to be 0, this number times a2 has to be 0. So that whatever that determinant number is, it's killing all those a's, right? It annihilates all of them. So now let's get serious about the other direction. So for the other direction, what we have is, so let's do 2 and 1 here. And this is, I really love this. This is what. So for 2 implies 1, what we have is, since UA is in A, and again, I'm going to assume A is generated by A1, A2, and N. What this means is if I multiply U by any of these generators, it has to be still in A. So U times any AI is a sum of all the generators AI. So I can write that this way, J R-I-J. Everybody agree? And that's just its containment here, because any unit of any AI must be a sum of those generators AI. And now I can write this in matrix form. And in matrix form, you get the following: U minus R11 minus R12 minus R13 minus R1N minus R21 U minus R22 minus R23 minus R2N. And finally, the bottom row minus Rn1 minus Rn2 minus Rn3 U minus Rn. Agree? I mean, you can just rewrite these equations this way, and that's exactly what you get. Matrix. And the determinant of this matrix must annihilate. A1, A2, all of these. Right? But the annihilator is 0. So determinant of these matrix correct. And if you take the determinant of this gives an equation. Right, because when you multiply this out, right, the determinant of this will be monic in U. It's just like your eigenvalue. And so U is simple. Right, that's kind of slick, right? So this is so yeah, there we go. Yeah, that's the tip jar. That's right, that's really slick. And this connection right here, next time I'll show you why, in fact, integral elements form a ring. Because once we've got this characterization in terms of modules, it's much easier to deal with sums and products. Okay, any questions? Yes, sir.
Let's just way back, and I missed it, but when you look at the example of the Gaussian integers, then you ask if A or B could be in Q minus C. And for the case of adjoining next to I, that can never happen. Then we looked at adjoining square root of -3. Is that the case we looked at, both A and B were in Q minus C? Is it possible to have an example where one of A or B is in the integers, but the other one is not?
That's a great question. No, not for quadratics. Yeah, and in fact, in general, it's true. You can't have this. You can't have just one row one in the post field here will not make it. Yeah. Thank you. Other questions? All right, you all have a good one. We'll catch you on the flip side.